and welcome everyone to the Cisco support community. Today we present a live Cisco support community Ask the Expert event. Our topic today, understanding Cisco ASR 9000 series aggregation services router platform architecture and packet forwarding troubleshooting. My name is Dan Gerson and I'll be moderating today's event. Our expert joining us today is Xander Taus. Xander is a principal engineer for the Cisco ASR 9000 series and Cisco IOS XR product family at Cisco. He is an expert and an advisor in many technology areas, including IP routing, WAN switching, MPLS, Multicast, DNG, ISDN, voice over IP, carrier Ethernet, system architecture, network design, and many others. He has more than 20 years of industry experience in carrier Ethernet, carrier routing, and network access technologies. Xander holds a dual CCIE in service provider and voice technologies. He has a Master's of Science degree in Electrical Engineering from Hogeschool van University in Amsterdam. Welcome, Xander. Our expert panelists today are CCIEs Alexander Vidakovic, Sadande Padki, and Krishna Iranti. They will help in answering some of your technical questions during today's event. Now, I'd like to briefly outline the format for today's expert series event. Our expert will start with a presentation on ASR 9000 for the first hour of the program, and then we will provide an answer to our today's trivia question of what do Cisco router technology, McDonald's, and Disney have in common. So stay tuned for that. Then we'll dive into the live question submission from the audience from the remainder of the event. During our live presentation, you may submit your technical questions to be answered by our presenter and the expert panelist using the Q&A box on the right side of your console. The team of technical experts is well versed in ASR 9000, so please begin posting your questions now to give us the best chance of answering them. If you experience any technical issues, please post those questions into the chat. We'll be asking polling questions today during this webcast, and we do encourage you to participate by answering them. If you'd like a copy of today's PDF presentation, you can download that using the link in the chat window. As an added bonus today, everyone who does join will receive 125 Cisco Preferred Access points. Now, let's get things started today with a polling question. What is your level of expertise with ASR 9000? A, I'm new to the ASR 9000 and iOS XR. B, I have a good understanding of iOS XR, but I am relatively new to ASR 9000. C, I have a good understanding of iOS XR, and I know how to work with the system. Or D, I'm using ASR 9000 already, and I'm pretty good with it. So go ahead and take a moment to answer the polling question. Don't forget, you can submit your questions at any time during the webcast, and we will cull those together and make sure we get to everyone's answer toward the end of the event. Now, I'd like to hand the mic to our expert, Xander, who will take you through the world of ASR 9000 routers and packet forwarding troubleshooting. Xander?
All right. Well, hey, good day, everybody. This is great. It's nice to see, that there are so many attendees interested in the ASR 9000. One of the things is that what we are trying to achieve with this program is, is that to give you a better understanding as to how the ASR 9000 works and what you can do with it and how it operates, so that when you have it in your hands and you may have a problem with it, configuring it or understanding packet loss or something like that, you know what to do and how to work with the system as you understand how all the components function together, right? So that is the target of today's session. So what we're going to go over is the platform architecture. The 9000 is composed of an RSP or a route switch processor. It has different types of line cards. We're going to talk to you about how the packet flows through the system and what different components are involved in the forwarding through the system, right? Now, as you may be familiar, we have several generations of line cards. We have the Trident or NP3 generation. We also have the Typhoon or NP4s, and we're going to differentiate between the two, so you'll be able to highlight and understand the difference between those two line cards. We're also going to talk a little bit about the feature order of operation. One of the things is that I find very important is that when you understand how features are being processed within the system architecture, you know what the implications are when you're linking several features together, such as an ACL and a QoS policy, right? We're also going to zoom in into the NPU architecture. The NPU is the network processing unit. It is the ASIC that is concerned with all the feature processing. We're going to zoom into that one really deep so you understand how that all works together. We're also going to talk about some scaling that is associated with the 9K. When you have Trident, what can you do with it, under what circumstances? And the same thing for Typhoon, and what happens when you combine those two generations of line cards together in the system. We're going to talk about the QoS implementation, so you have a good understanding as to, what the quality of service capabilities of the system are, and how the system works with that all together. QoS is one of the features that is very hardware dependent, because different platforms within Cisco, or even, platforms between vendors, operate or implement QoS in a very specific manner. And we want to highlight kind of, the architectural implementation for the 9K. Finally, we also want to talk about the FIB or forwarding information base. That is basically the routing architecture of the ASR 9K, so you have a good understanding of that as well. Unfortunately, considering the time that we have, which is only an hour, we don't have that much time, to go into the operating system of iOS XR, but we'll save that topic for a next event, because, that might be very interesting to talk about some other time. All right. So, when we're talking about the ASR 9000, what is it composed of? The two main platforms or chassis that we are currently carrying today is the 9006, which is a 4-slot 2RSP device, and we have an 8 line card slot with 2 RSPs in the 9010. There are two ASR 9000s not drawn in this picture. That is the ASR 9001, which is a very small ASR 9000, built on the same technology and architecture, and I want to say that is the next 7200. So versatile and super powerful. There is another big brother there that is not being drawn. That is the 9922, which provides you for 20 line cards and has separate route processors and switch processors, in the middle of the chassis. So when we are zooming into the ASR 9001, of the ASR 9000 platform architecture, basically we have two key components here. Those are the line cards and the RSPs. The RSPs is the route switch processor. And why do we call it a route switch processor? Well, basically the control plane CPU as well as the fabric are residing on the same logical blade effectively. Even though the fabric is residing on the RSP, it is completely logically separated from the control plane. What does that mean? If the route processor or the control CPU would crash for whatever reason, or has a process crash, it would not affect the fabric forwarding at all. So that is a key concept within the ASR 9000 architecture. Also, the route processor runs an operating system known as iOS XR. That is the next generation, as opposed to, the classic iOS that you're familiar with. And iOS XR is kind of a Linux-based operating system on which every functionality and process is running as an individual entity on the machine, or on the kernel, so to speak, which means, that if there is a process level failure, it is contained within that process and it doesn't affect any other thing. So one of the things that you may have seen in iOS, so unfortunately, is that the whole device goes down. iOS XR generally never goes down by itself. It may have a process crash on its own, and that will not affect the forwarding of the system altogether. So that is kind of one of the key implementations here for the 9000. On the left-hand side, you see two types of line cards being drawn here, and they are basically pictures of the NP3 generation. And you see a 40 gig line card here and an 80 gig line card. Why can we tell the difference between the two? Well, basically, we see on the 40 gig line card, we have one FIA, or Fabric Interface ASIC, whereas on the 80 gig line cards, we have two FIAs and they're basically connecting to the fabric of the RSP. When we're talking Typhoon, pretty much the same picture applies, although there is a little switch fabric on the line card itself, but we'll zoom in into that as we come to the NP4 architecture. So basically, the 40 gig and 80 gig line cards are composed of physical interfaces, and that is basically defined by the faceplate of the line card. And then we have the NPs that you can see here in the picture, and those are the network processing units, or NPUs, also known as Trident or the next generation Typhoon. And those are the actual guys that do the feature processing for us, that feed their packets into the FIA or the fabric interface ASIC, which will hand them over to the fabric, and they will be switched to the destination line card. One thing that I do want to mention also about this picture is that you can see that there is a CPU drawn on the line card, which means, that the 9000 is a fully distributed platform, and that allows us, to outsource a lot of local activity to the line card CPU, as opposed to, having that dealt with by the control CPU on the RP or on the RSP for that matter. Functionality that has been distributed to the line cards that is pretty much local to the line card are things like BFD, for instance, or NetFlow, or a CFM, Connectivity Fault Management. That is all handled by the local line card CPU, and that allows us effectively, to increase our scale significantly in that regard. Okay. Let's look at the chassis real quick, just to give you a quick impression. The 9006 is a side-to-back airflow system. The 9010 is a front-to-back airflow system. And the reason why that is important is because we get a lot of questions, because when you're installing 9000s or any network product for that matter in data centers, space is key, right? And we want to put as many chassis as we can into a single space. So one of the questions that we have been getting frequently is that because the 9006 has a side-to-back airflow, whether you can put them in racks adjacent to each other. And that is no problem at all. Because, if you have a perforated front door and you have an air buffle that basically redirects the airflow from the front to the side and allows it to exhaust on the back, you can pretty much, stack all the 9006s next to each other. There should be no problem with that. Both systems have 2 fan trays and room for 6 power supplies on a 9010, or even 8 when you have the V2 chassis, and we'll zoom into that a little bit later also what the differences are there. And the 9006 has room for 3 power supplies, or 4 in the V2 chassis mode. So when we're looking at the power distribution, this is also one of the important concepts. For those of you familiar with the 7600 series router from Cisco, the 7600 has power modules that feed a particular area of the chassis. In the ASR 9000, we backed away from that particular model, whereby each power module is effectively feeding its power into the power distribution bus, from which all the line cards, RSPs, and fans are being powered. So there is no physical dependency as to where you would want to put your power supplies in. However, what we do want to recommend is that if under a particular configuration, you require 4 power modules, because, it is all pay as you grow. So you don't have to fully load the power modules into the system. If you have a particular number of line cards and you have not fully loaded your chassis yet, and the power requirements tell you that you have to have 4 power modules, you can effectively stack them as power supplies 0, 1, 2, and 3, or you can load them as 0, 1, and 3, and 4. Well, that latter one would be the recommended power configuration for us, for this simple reason, that if you were to load the power modules 0, 1, 2, and 3, if power module 3 would fail in its own shelf, the shelf doesn't know anymore whether there is a power module present but failed, or whether there is no power module present at all. So if we are loading the power modules 0 and 1, 3 and 4, and power supply 3 would fail, well, power supply 4 would still feed, say, sort of the shelf, allowing it to detect that there is a module present in module 3, but it is non-functional. So that allows you for a better management of the system. Basically, what I forgot to mention is that this picture shows you the AC implementation. The difference between AC and DC is that AC power modules only have a single feed, so a single power cable, so to speak. And that gives you effectively one-to-one protection in case you have dual AC feeds, right? Because if feed A in this picture would completely fail, feed B would take over, and that gives you one-to-one redundancy. In the DC mode, the DC power modules have the ability to, with dual feeds, so you can basically give the feed A and B onto the same power module there. If feed A would completely die, the modules, are basically being fed by feed B, so this is giving you end-to-one protection on your power modules. The one question that we are always getting here is, like I said, what would happen if I provide both feed A and B, and a module would draw, let's say, 10 amps. In that case, both feed A and B would provide about 5 amps to the power module. But that also means is that you have to allow the breaker size to be set to the maximum possible draw, which is in this case 10 amps, and so to speak, because if feed B fails, feed A would have to provide the full 10 amps of power draw. So even though they load share, you still have to provide the right breakers on, or the maximum breaker size on the power modules. We have two generations of RSPs, or route switch processors, for the ASR 9K. That is the RSP2 and the RSP440. And basically the key difference between the two is outlined here in this quick picture, and let us go over that real quick. The RSP2 gives you a dual core Freescale processor, whereas the RSP440 has a quad-core Intel processor. So as you may have seen already when downloading software for the ASR 9K, you have seen the -P images as well as the -PX images. Well, basically that comes from the different types of CPUs that are on the RSPs, right? So the -P is linked to the RSP2, the -PX is linked to the RSP440. Now, it is important to note that starting XR430, which came out of December of last year, we have combined the two images together, so you will only see the -PX image available, which is then suitable for both the RSP2 and the RSP440 for any XR images larger or, in quotes, older than XR4.3. The RSP2 has control CPU memory, and you have two flavors here. That is either a 4 gig or an 8 gig version, whereas the RSP440 gives you a 6 gig and a 12 gig version. And the two different flavors of the RSP are denoted by the -TR and the -SE, as you can see highlighted in red. TR stands for transport, SE stands for service edge. The main difference between the two is, in quotes, the scale that those guys can provide, right? So when we're talking about the different line card variants, and you'll see that coming soon as well, Typhoon line cards have the same time of denomination with a -TR for transport and -SE for service edge, which basically gives you different scale on the same type of line card architecture. There is, of course, a cache present, great marketing numbers over here. Primary storage, that is a USB disk that is split in two types, 2 gig on the RSP2. One important thing to note here is that at this point in time, those 2 times 2 gig are mirrored with each other, and those are designated by disk 0 and disk 1. Disk 0 and disk 1 are the primary storage on which you are loading your iOS XR image, from which we will be booting the main image. Starting XR431, which is going to come out next week effectively, we are able to break that mirroring effectively, giving you 2 times 2 gig independently to be able to use from each other. So disk 0 and disk 1 can be used separately, which could not be done before. On the RSP440, this is a 16 gig solid state disk. The secondary storage is well, in this picture it says a 30 gig hard disk. It's a spinning hard disk on the RSP2, but you can see different flavors of that. You can see also 70 gig or 100 gig, depending on what size was available from our vendors. Basically, the hard disk is being used for your vacation pictures as much as, like crash dump blocks and other storage that you may want to use, for instance, for field programmable devices. On the RSP440, this is a 16 gig solid state disk also. Another difference between the RSP2 and the RSP440 is the fact, like that the RSP440 now has a USB port. And that is a very handy functionality that if you want to go on site and you have all your images and smooths and whatever else you want to load on the RSP available on a memory stick, you can directly push it into the RSP440 and boot from that. The RSP2 did not have the USB disk. Instead, it had a compact flash. And that was basically there, like it's because pretty much every Cisco platform has a compact flash, so we put it on there, just for legacy reasons. Other things, highlight to note here is that the NV cluster or Ethernet out of band connection. What the Ethernet out of band is, we'll look into shortly as well. And basically, it allows you to extend the control plane out of that EOBC port to another ASR 9K physical chassis, and you'll be able to link two independent chassis and make them one logical entity. CRS, for instance, calls it multi-shelf, or Nexus 7K calls it VSS, right? Those are comparable things. The fabric on the RSP2 provides for 184 gig per slot, whereas on the RSP440 it gives you 440 gig, and we'll see, how those numbers come about. This picture shows you what the general architecture of the RSP engine is, and more specifically, what you see here on the faceplate. You see here on the left-hand side that there's a complex flash card drawn, and that basically shows you that this is an RSP2 layout, but the RSP440 is not much different than that, except for that the faceplate has changed, and that the actual CPU changed from a Freescale dual-core to an Intel quad-core, right? Here you can also see that the CPU has an Ethernet switch that is known as the Ethernet out of band. What that means is that every time the CPU processes, let's say, a BGP update, and it recompiles the routing table, and it wants to update the sex tables on the line cards, well, basically, that results in a message over the Ethernet out of band that is being handed over to all the line cards, who are then programming the new routes on their NPUs for the updated forwarding. Another thing is, there's an I/O FPGA that gives you access to the NVRAM, boot flash, auxiliary port, and alarm interfaces. The I/O FPGA is one of those FPDs that may have to be updated during iOS XR upgrades. So when you're talking about iOS XR upgrades, sometimes there is a necessity of updating FPDs or field programmable devices, and the I/O FPGA is one of them. One other thing that you can see here is that it's in the gray box on the right, on the bottom right. Which is where you see the two crossbar fabric ASICs. That is the actual fabric of the 9K. And there you see a fabric interface ASIC talking to a punt FPGA that has access to the CPU. So what you can glean from that is that the fabric is indeed logically separated from the whole control plane, and the control plane basically requests access to the fabric as any other line card would. Now, one thing that is also very important to mention here is that these management Ethernets that you see here on the left-hand side, they are talking directly to the CPU, and by default, the CPU restricts access from these management Ethernets to the punt FPGA, which effectively means that packets coming in on the management Ethernet can never be routed out to a line card interface. And the same thing applies in reverse too. A line card interface will be able to send packets punted to the CPU, like a BGP update or an OSPF hello or what have you, but it will never be able to be routed out to the management Ethernet. That is part of what we call the local packet transport services or control plane policing, whatever concept you prefer, and that is part of the system embedded security. A quick overview of the different line cards that we have today. On the top portion of this slide, you see the first generation or Trident NPUs, and we have 6 different kinds of that. That is a 40 by 1 gig, a 4 by 10 gig, an 8 by 10 gig, but oversubscribed. What the oversubscription means, we'll show you in a minute also. There is a combo card that is 20 ports of 1 gig and 2 ports of 10 gig. And the last 4 cards that I mentioned are following the 40 gig line card layout. So they have 4 NPUs and 1 FIA. The two cards on the right-hand side is the 8 by 10 line rate and the 16 by 10 gig, which is then again oversubscribed. But those are the 80 gig line cards that effectively give you 8 NPUs and 2 FIAs. All those line cards that we're talking about here come in 3 different scale flavors, and that is being denoted by the suffix on the line card identifier, and that either be the -L, -B, or -E for low queue, base, or extended memory. We'll talk about that, what that precisely entails. But in the bottom hand of this slide, you see the Typhoon or NP4 or next generation line cards. And of that, we have the 24 by 10 gig E, 2 by 100 gig E, 36 by 10 gig E, and we have 2 modular line cards. That is a Mod 80 and Mod 160. The difference between those two is that the Mod 80 has 2 NPUs and the Mod 160 has 4 NPUs. So that either means, that you have 1 or 2 NPUs per bay. And these bays can be filled with any type of what we call MPA or modular port adapter. And we have the flavors of a 20 by 1 gig, a 2 by 10, a 4 by 10, a 1 by 40, a 2 by 40, and we also have an 8 by 10 coming out as well. So, looking at what the 40 gig line card architecture precisely looks at, is that the core of these line cards is the NPUs 0 to 3, and they are doing the feature processing for us. Then we have the fabric interface ASIC, and that guy connects to the crossbar ASICs on the RSPs. As we saw in the RSP architecture, we basically have 2 crossbar ASICs per RSP, and each of those blue arrow lines to the crossbar ASIC is a 23 gig link for an RSP2 connecting to a 40 gig line card. So you can see here that on a single RSP, 2 times 23 is 46 gig, which is more than sufficient to drive this line card to full line rate. If I have dual RSPs, then basically I can give you a 96 gig worth of fabric bandwidth, which is great, but the NPUs themselves, can't, generate that much traffic. So the bottleneck will then be the NPU itself. Not only the NPU, but if I only have, a 10 gig PHY connecting to an NPU, this line card will never be able to generate more than 40 gig traffic. So when we're talking about the 8T/4 line card, which is the 8 by 10 oversubscribed card, what basically happens here is the IO daughter card that you see here on the left basically connects 2 physical 10 gig PHYs to the same NPU. The NPU or Trident can do 15 gig worth of traffic, and if I do 4 times 15, that line card would be able to give you potentially 60 gig of traffic. And then if we're looking on the right-hand side again, 2 times 23 on a single RSP fabric bandwidth gives me 46. So in this oversubscribed line card, I may want to have 2 RSPs to reduce the level of oversubscription. Basically, giving me 96 gig of fabric bandwidth, and then my limitation would be the NPUs again, that basically give me 15 gig per NPU or 60 gig total for the line card. One thing that I haven't talked about yet is this green square that is sitting there in the middle. That is a bridge FPGA. You can ignore that guy for any forwarding implications, because the bridge FPGA just converts the memory interface of the Trident NPU towards what the fabric interface ASIC wants to see. And that is an XAUI to DDR2 conversion, in case you're interested about knowing that. Well, the 80 gig line card basically doubles the picture as what we saw in the previous slide. Instead of 4 NPUs, we have 8 NPUs, and instead of 1 FIA, we have 2 FIAs. And here you see also is that if I were to have a single RSP here, I still have 4 fabric links of 23 gig, which basically gives me 96 gig of fabric bandwidth, which is more than sufficient to drive this card to full line rate. So you may ask, why would I want to have, dual RSPs? It is basically for redundancy, right? If one RSP would fail or there is a failover necessary, basically, the control plane fails over, and you still have, all your fabric bandwidth available. So dual RSPs just give you, an increased level of redundancy. However, you don't need it in order to drive these cards to line rate. So looking at the Typhoon-based line cards, it's pretty much the same logic, and this is personally what I love about the ASR 9K, right? Is that once you know one line card and one architecture of the line card, you can basically, like apply that to any other line card that you that we have, because the whole forwarding procedures are still the same. So basically, the layout for Typhoon or NP4 based line cards is that the NPU is still connecting to an FIA. However, to reduce the number of fabric links that are going from the line card to the RSP's fabric, we had to insert a fabric on the line card in order to reduce the number of fabric links. Because, and we'll see that in a minute too, on the 24 by 10 gig line card, we have, like a large number of FIAs, and the number of fabric links that the FIAs would generate, we just don't have enough switch ports on the RSP's fabric for that. So there is an intermediate switching stage on the line card to reduce that number of fabric links. So this is a picture of the 24 by 10 line card. We have the Typhoon NPU, and we have 3 10 gigs connecting to that NPU. We have 4 FIAs serving 2 Typhoon NPUs, and then as mentioned, we have this switch fabric ASIC. And if you have the next generation RSP or the RSP440, basically it gives you 55 gig fabric links. And per RSP, you basically get 4 of them, so 8 in total. So 4 times 55 is 220. Bidirectionally is 440. This is where the RSP 440 comes from, or the ability, to give you 440 gigs per slot. If you have dual RSPs, then basically you double that number, right? So you have effectively, instead of 220 gig per direction, you get 440 gig per direction with the RSP 440. Also, you see here the switching fabric inserted on the line card, basically, as I mentioned, to reduce the number of fabric links. What you also want to take out of this picture is that I mentioned that the Trident NPU is about 17 million packets per second each direction. That gives you about 15 gig worth of bandwidth. The Typhoon NPU is about 44 million packets per second, or it can produce about 60 gig or almost 60 gig of bandwidth, depending on your packet size, obviously. So what you can get from this line card is that this is very heavily over-engineered line card, because you only see 10 gigs or so, potentially 30 gig of bandwidth requirement on this NPU, which can potentially provide 60. So this card is really designed, to give you, the maximum power under pretty much any feature combination that you can think of. If you want to go a little bit lower key, we also have the 36 by 10, which basically gives you 6 10 gigs per NPU. And as I mentioned, this NPU can drive about 60 gig and still 44 million packets per second. So this line card gives you a higher density of ports, but at the same time, that it can still drive line rate. That should be no problem either. But every feature that you enable on the NPU or on the interface, for that matter, will decrease its packets per second performance, which inherently means that your minimum packet size to reach line rate will go up. All right. So while the 24 by 10 can do 64 byte line rate on 10 gig, the 36 by 10 will give you at about, a 170 byte minimum packet size in order to reach line rate on all 6 interfaces. The 2x100 line card follows a slightly different architecture. The only key differences here is that the Typhoon NPU can do 60 gig each direction. If we make it in a simplex mode, it can do 120 gig or 90 million packets per second. And that's what we're doing here for the 2x100. That effectively each NPU serves one direction only. So we'll have a MUX demux, which is the blue box that you're seeing sitting in between the NPU and the FIA. But from the FIA on, it is still the same type of architecture that you've seen before. The modular Ethernet card is a very simple architecture again. We have the FIAs. We don't have to go discuss that again. We have 4 NPUs on a Mod 160. And if I move to the Mod 80, you basically see that we only have two NPUs here, and that is basically serving you one Typhoon per bay or two Typhoons per bay. So if I were to have the Mod 160, let me go back one slide, and I would insert a 4 by 10 gig NPA in this bay, what would happen is that two 10 gigs would be served by one Typhoon and the other two would be served by the other one. So the reason for having this card is that you can basically, if you have the requirement to have a very intense feature set and you want to have optimum performance, the Mod 160 line card is what you want to go for. If you want to go for a lower cost option, you can also use the 4 by 10 gig E on a one Typhoon, bandwidth-wise that is perfectly possible, but if you have a heavy feature set, you may not get the 44 million packets per second anymore, as that might go a little bit down as you enable new features. Packet flow through the system. This is a very important piece here because, like I said, what I want you to get out of this picture is that every packet that is being received goes over the fabric of the RSPs. So even though one sub-interface may talk to another sub-interface on the same physical interface on the same line card, packets still go through the switch fabric of the RSP. And even though there is a switch fabric on the line card also, we still switch everything through the RSP. So that local switch fabric on the line card is only to reduce the number of fabric links between the line card and the RSP. We have talked a little bit about the ASR 9000. I did not have a picture for you, but you may be familiar with this platform already. What this basically is, it is an RSP and a Mod 80 line card slapped into a 2RU system, right? And basically, it gives you 4 onboard 10 gig E's. They are fixed. And we still have the 2 bays like you have on the Mod 80. And basically, you still have, like a line card CPU and an RP CPU, similar as that what you would have, like with one line card and one RSP. And also, there is still a switch fabric here in this little box also. And you might wonder, is this really necessary? Could you not have linked those two FIAs together? Yes, technically, we could have done that. But we chose to do this architecture here to make sure, that every ASR 9000 follows the same type of architecture so that the troubleshooting and understanding between all platforms and all architecture is pretty much still the same. So you don't have to relearn new platforms all the time. And the same packet flow applies here too. Every packet that is being received goes through that switch fabric complex on the, in quotes, RP portion of the 9001. So we have talked about the different line card memory options, right? And those are high, medium, and low queue for Trident, or service edge and transport, or -SE and -SR for Typhoon. And basically what they mainly change in terms of scale is the QoS scale and the layer 2 sub-interface scale, or EFPs, or Ethernet flow points is what we call them, or switch ports for that matter. What doesn't change between those two cards is the number of routes that you can have on the system, number of MAC addresses, bridge domain, layer 3 interfaces, or VRFs. So all the L3 stuff doesn't really change effectively between the different flavors of cards that we have. So what basically determines what scale line card you want to go for is that how many QoS queues you are acquiring per interface, or whether that be a sub-interface or not, and how many interfaces you want to be able to configure on that line card. So where does this scale precisely come from, right? Is that if we're zooming in a little bit more into the NPU portion, there are different memories attached to that NPU, and that is stats frame memory, TCAM, and lookup memory. So lookup memory on Trident is shared between L2 and L3. Which basically means that you have to predetermine how you would want to use the Trident line card as a layer 2 line card effectively with a lot of max scale, or maybe you would want to use it as a routed platform, like for instance for your MPLS core or what have you, and upon which you may want to favor the FIB space deviation on the lookup memory more. On Typhoon-based line cards, this lookup memory is completely separated, which basically gives you the same number of L2 scale and L3 scale separate from each other. Now, if you have statistics memory, stats memory is basically used for, basically what it says, right? Interface statistics, QoS policy map statistics, show interface counters, and what have you. If I have more memory of that, I can support more interfaces, simple as that. Frame memory, if I have more frame memory, I can buffer more packets on the line card. And TCAM, if I have more TCAM, I can basically support more interfaces because I use the TCAM for VLAN matching. It's not being used for the FIB, unlike the 7600, for instance. I can also have larger QoS matching scale, and I have larger ACL scale if my TCAM is larger. So that is basically, and those three green portions of the memory is what is changing between LB and E cards or TR and SE cards. So hopefully that makes sense now. A quick overview as to what different scales you can expect from these Trident-based line cards. I don't want to go into them individually. This is nice for future reference, probably. We don't have that much time left, so I want to go, into the main portions of this presentation too. This gives you a great overview of what the difference between the transport and service edge Typhoon-based line cards is. And here you can basically see, that the FIB scale went up from 1 million to 4 million, and the number of MAC addresses went from 512K to 2 million. And those are the key scale increases on the Typhoon-based line cards. Oh, another polling question for you. How are you using the ASR 9000 in case you have this beautiful product already? So, all right, let's look at the fabric real quick. Basically, we have talked about the FIA, and the FIA is the fabric interface ASIC that connects you to the fabrics residing on the RSP. If you have the RSP2 or Trident-based line cards, these fabric links are 23 gig each. If you have the Typhoon-based line cards or the RSP440, they can provide you 55 gig worth of bandwidth. Another thing is that the fabric interface ASICs, and we'll zoom into this little piece of hardware in a minute also, is that they have what we call VoQs, or virtual output queues. And each 10 gig entity within the system is represented by this by a VoQ entity. So the FIA basically requests, grants, or schedules its packets that it wants to send over the fabric based on that in quote shape rate of 10 gig of 10 gig of VoQ bandwidth within the FIA. The way that it would work is that the FIA requests a grant from the arbiters on the RSP. The arbiter basically provides a grant back. The FIA then schedules its packet on one of the 4 fabric links in case you have dual RSPs available. And that is being load balanced based on, for Unicast it is load balanced round robin. For Multicast we basically hash the S, G or source and group addresses, and we put the whole Multicast flow onto a single fabric link. And this is to maintain flow integrity. Once the packet is being received by the Ingress line card FIA, the credit is being returned to the arbiter. And this picture basically shows you, like I said, how we are load balancing the traffic over the different fabric links available. Each packet, or I should say each super frame that is being transmitted over the fabric links has a sequence number in there so that the receiving line card can always put them back in the right order. So we will maintain flow integrity when packets are being forwarded over the fabric. As I mentioned, Multicast is being load balanced based on the S, G, and this picture basically tries to show you how that looks visually. Now, one thing, and as you heard already, I misspoke myself almost there by saying, each packet going over the fabric, and that is an incorrect statement because, it is a super frame that goes over the fabric. What is a super frame? Well, basically, in order to make the optimum use of the fabric forwarding, we try to aggregate small packets together into what we call a super frame, so that we only have to ask for one grant to one particular destination line card. And this significantly improves the switching performance of the whole fabric. Now, if we have waited in quotes a little bit of time, and I'm talking microseconds here, right? So it is not that long at all. So if we cannot aggregate multiple packets into one super frame, well, we basically ask a grant for that individual packet, or maybe 2 packets that have been aggregated together. So why is this important? When you are doing the packet troubleshooting through the system and you look at your fabric links and you see that there are only you see the number of 100, that is basically the number of super frames that the fabric has transported, right? So even though your Ingress interface may have said, hey, you received 200 packets, and you see the number 100 going over your fabric, it doesn't mean you lost 100, right? It could potentially mean that you have aggregated 2 packets together constantly. So there are different commands available, and we'll talk about it in a little bit more also, that can show you, like if the fabric has dropped packets, if at all, but that generally doesn't happen. All right. So I talked about these VoQs already a little bit, and this picture, tries to highlight how that logically works, right? So in Trident, an NPU is basically capable of forwarding pretty much like 10 gig. And each NPU in that case is being represented by a single VoQ set. And these VoQs consist of a priority 1, priority 2, best effort, and multicast. Multicast not drawn in this picture. And the great concept of that is that when one particular destination or one NPU is getting overloaded, it can tell the Ingress line card or line cards to say, hey, my default class is getting overloaded, stop sending me any more of that traffic, while it can still accept, for instance, high priority traffic. So basically, that allows you to, 1, guarantee high priority traffic being transmitted end to end, and at the same time, one particular destination that is getting overloaded will not flow off other destinations, and that is what we call head of line blocking, right? And that is what this picture is trying to show you, is how these VoQs are implementing that particular concept. Okay, so this is a great slide. I forgot that I had that one available here, but this shows you, like I said, how that head of line blocking basically works, right? So in this particular example, we have 2 blue flows of 10 and 15 gig going to the same destination interface, as you can see here on the right side, right? And that basically means, like I said, that NPU is getting overloaded because 15 gig is way too much for that 10 gig PHY, so we have to flow off something. But what we're doing is we're only flowing off that particular class default VoQ. So if there is another interface or saying, like I say, hey, I've got this green flow here that needs to go to a completely different destination, that particular flow is following a different VoQ and is not being flowed off. So this is what that head of line blocking mechanism looks like for the ASR 9000. At the same time, and let me make sure that you understand, if there were to be a high priority voice over IP stream or what have you, having to go to NPU number 0 of egress line card number 2, so basically following the blue line direction, we can still forward it towards that NPU because, like if the best effort queue is only flowed off and not the P1 and P2. All right. So, feature order of operation. This is an important one also because here you can see effectively the processing associated with the Ingress line card and the egress line card. So let's go over that real quick. I want to mention also is that we have written a lot of tech notes, like that talk about these particular topics. And if you were to Google ASR 9000 feature order of operation, you'll probably see this picture reappearing, with a lot of more detail than I'm able to provide here today due to the time constraint, unfortunately. So we have interface classification, what type of VLAN are we dealing with, what interface is that associated with, because that allows us to derive what type of features are associated with that particular interface. If there is an ACL applied to that interface, we are going into the classification, and the same thing for the QoS classification. And these two guys together basically, result in the same TCAM lookup, right? So in the first stage, we are making the key for the TCAM, we'll send it off to the TCAM, and we're getting a result back. We are not doing anything with that result yet. So we're doing a forwarding lookup, which basically gives us the ability to see, like I said, hey, to which destination line card do we need to go? Then we have an IFIB lookup or an internal FIB. As you saw from the earlier slides, the 9K is highly distributed, and that means, like I said, if the packet is for us, we can direct it to either the local line card CPU, or maybe it has to go to the RP. And that is basically what the IFIB lookup gives us. security ACL action. So if we derive that we had an ACL and an ACL needs to be applied, the action is being taken out over here, and that basically you can see here that the QoS policer action follows later. So what you can get out of this particular sequence is that if a packet is being denied, but also, like is subject to policing, the policer would not even see this packet anymore because the security ACL action is being done before that. So that's why that feature order of operation is so important, right? Layer 2 rewrite, that basically applies the switch fabric header. The QoS action, whether that be QoS shaping or weighted red, is being done over there. And the IFIB action, so here is basically whereby we direct that packet towards the punt path. And here again, right, if a for me packet is subject to policing or ACL, that packet will get denied in the hardware. So when I'm applying an ACL that denies telnet, for instance, to my loopback interface, I can drop these packets in hardware already. And that is something, like that is very platform specific, right? Okay. So when we're going into the NPU and zooming a little bit deeper, is that all these different functions, are being handled by different stages inside the NPU. And those 5 stages are known as parse, search, resolve, and modify. And then the queuing and scheduling is being handled by the TM or traffic manager. So each of those stages is concerned with a different operation, tied to the packet handling. And the reason why I have this visualization here for you is that when you are looking at the NPU with the command show controller NPU counters, you may see that word parse or modify or search in there. And basically, it allows you to understand now where that counter is being generated. And this basically, helps you pretty much understand where that comes from then. So the forwarding of the forwarding architecture of the NPU is shown in this particular case, right? And the reason why I want to show you this picture is because this is one of the other great implementations that we did on the 9K, right? Is that a packet comes in from the wire. We use a TCAM for packet classification. Remember, not routing, right? Because routing resides in the search memory. Basically, the TCAM provides us what we call the RX IDB, or Receive Interface Descriptor block. And that IDB is just a structure that provides us all the features that are applied to that particular interface, right? Then we're going into the L3 FIB, trying to find out, is that what destination we're going to, right? That is pretty clear. And that gives us, a quick, what we call RX adjacency. And the reason why we are doing that small FIB lookup on the Ingress line card is basically we want to forward that packet only to one line card and not all of them, and the majority of the line cards can't even forward it, right? And that same thing, applies to when your egress interface is an ether channel or port channel, or what we in the 9K call lag or link aggregation, right? Or bundle Ethernet for that matter. So if you have multiple members on multiple line cards, we only want to forward this packet to that particular line card that is having a member that is going to forward this packet for me. So that's why we are doing that hash computation on the Ingress line card. Then when the packet goes to the egress line card, we basically do another FIB lookup here, because effectively we need to get our layer 2 rewrite string, right? We need to find out what the destination MAC address is, whether there is a VLAN header to be applied or not, whether there's an MPLS encap to be applied. Now that is what the TX adjacency gives us. Now one thing that is very important to get out of this picture also is that the RX adjacency lookup is much lighter than the TX adjacency lookup, because TX adjacency goes all the way down. So when we are doing a feature called Unicast RPF, we need to find out in the routing table whether the source address is indeed found via this interface that I received the packet on. So my RX adjacency lookup basically has to go down all the way like the TX adjacency does, and that is a significant performance impact, of course. But then you, hopefully now you understand, why features like URPF, are so intense for hardware forwarders. Anyway, is that there is still a lag hashing computation being done, and the reason for that is that this particular NPU may have the 2 members itself, and now we want to find out which member to use, of the members that are attached to that particular NPU. This is basically, like giving you an example of how to get the UIDB or interface descriptor block. The U stands for micro, whatever. And this command shows you basically, like how to get that info forward. I see that it is 12 o'clock already. We want to reserve some time for the Q&A. Allow me to finish for 10 more minutes, talking about the FIB architecture. This, what you see here being drawn, is what we call a subtree implementation, and that is the implementation that the Trident NPU follows. What you can get out of this picture is that when you have a VRF number 0 to 15 or table IDs 0 to 15, they basically have a subtree per /8 network. And a subtree size is about 256k prefixes, so we can effectively load 256k prefixes per /8 for the first 16 VRFs that we have available. And table ID 0 is a global routing table, right? Now, in the end of the day, that subtree effectively leads us to, hopefully, a non-recursive prefix leaf. And a non-recursive prefix leaf is basically, like gives me a direct next hop. But a recursive prefix leaf in this context is kind of, like a BGP route, right? Because a BGP prefix may say, is that, hey, my BGP next hop is address 1234. And in order to get to 1234, you need to send it via my interface 10 gig 0001 with this particular L2 rewrite string. So a recursive leaf is basically a BGP next hop, if you will. And in the end of the day, your recursive load distribution index, that's what LDI stands for, points to a non-recursive leaf. Now, here also, if you were to Google ASR 9000 route scale architecture, we are going into much more depth as to, how the subtree implementation for Trident is. One thing important to note is that Typhoon NPUs fortunately follow the mtry logic again, and mtry basically is the same thing, as what many iOS Ceph routers implement. So they don't have these subtrees and subtree sizes implemented anymore. Okay. So one thing that I do want to point out about this FIB implementation is, because this is another great concept, like that 9K and iOS XR basically give you, right? Because we were talking about the recursive prefix leaves, the BGP route, so to speak. And they can point to a non-recursive route, which is, like my IGP next hop, okay? And my IGP next hop may be a bundle interface, right? With so many different members in there. And here, but what is so important about this picture is that when one of my BGP next hops would fail, right? If I do BGP load balancing, I don't have to update my whole non-recursive leaves. No, what I do is I just flip that pointer over here from the recursive LDI to a different non-recursive LDI, and this is what we call PIC, prefix independent convergence. So instead of having to touch each individual BGP prefix and rewrite that BGP prefix, I just flip a single pointer in order, to make the convergence happen, and I do that immediately for all the BGP prefixes that leverage that that next hop. At the same time, I want to point out that the numbers that are being quoted here, 8 ways recursive, is a Trident number. It's 32 ways for Typhoon. For the non-recursive or IGP load balancing, that is 32-way, and that is 32-way between Trident and Typhoon. And then each leg, or bundle Ethernet, or port channel Ethernet channel, can consist of 64 members. And here again, right, even if I have a member appearing or disappearing, the only thing that I have to update is my lag table. I don't have to touch all my prefixes individually. And that is a key difference between the 9K and XR implementation as what you have seen, like potentially in many other Cisco platforms, or maybe from other vendors too. So, okay. Some words about load balancing. This is also, like a very important concept, right? And in this case also, we have a great article available. If you were to Google, in this case, ASR 9000 load balancing architecture, you will be able to find a very decent write-up, like as to what you can expect from the load balancing. Because, hey, if we have, like 32 IGP paths available, how are we going to use them, right? Well, it really depends on the type of encapsulation that is being used in this case. So let's go over the various scenarios here real quick. If I have IPv4 Unicast to IPv4 Unicast, right? Or maybe IPv4 to an MPLS core. In that case, like is that we will use the L3 source and destination addresses. If there is a known layer 4 protocol available, and that being TCP or UDP, we use the source and destination ports also, and then we feed that together with what we call a router ID or RID. And that is basically, like the A-loop back interface, like that you can, that is defined on the system. The reason why we feed a router ID or a RID into this hash computation is to get some sort of per node variation in the hash computation, right? Still, this might result in polarization when you have a chain of XR devices or 9K devices in your network. Fortunately, we have this capability to shift the hash result based on a configurable number, and that basically follows the logic back what we used to have in iOS Ceph, right? With the iOS Ceph load balancing methodology of tunnel and universal and stuff like that. When we are doing MPLS to MPLS or MPLS to IPv4, MPLS to MPLS is basically label switching, right? Or on your P routers. And if you have MPLS to IPv4, that is basically on your PE router, where on the downstream direction, packets received from the core and going to your CE, for that matter. In that case, like I said, we are looking at the number of labels here. We can pop 4 labels in one go. If you have more than 4 labels, we get what we call recirculation in 7600 terminology, or what the PXF called a feedback, right? Nothing problem with that, adjusted cost you packets per second performance. Either way, if we have less than 4 labels, and if the inner is IP based, then we will follow the earlier case 1 scenario. If we are not detecting IP in the after the inner label, and that can be the case when we're having an Ethernet over MPLS pseudo wire, right? What will follow after the inner label is basically an Ethernet header. So in that case, like I said, that we will not be able to do IP-based load balancing, and then we'll follow, and then we'll use the inner label with the router ID. And here is the other important part, right? Because that inner label can be a FET pseudo-wire label also. And the FET pseudo-wire label is being inserted by the PE routers that you have. And the 9K acting as a PE router is perfectly capable of that. If you don't insert a if you don't insert a FET label, basically that 4th label for an Ethernet pseudo-wire will be your pseudo-wire ID label, right? Bundle load balancing. So if we are having an Ether channel, basically, if we are having a routed bundle, so that is basically an Ether channel with an L3 interface on it, we are following case 1. So that is L3 and L4 information with the router ID. If we have an MPLS-enabled bundle interface, we follow case 3 as in a ECMP load balancing. However, and this is important, ECMP and bundle, even though they leverage the same hash computation, we are just using different bits out of that hash in order to derive the member or ECMP path, right? So it is not said, like that if path 1 is being chosen in ECMP, that member 1 will be chosen for bundle. So it's different bits. If we are having a layer 2 bundle, that basically means that we have a switch port defined as an Ether channel going to a CE device. Then, by default, we are using the source and destination MAC and the router ID. If I don't want that, I can also use L3 information if I configure the command L2VPN load balancing flow source destination IP. And that's when I leverage the L3 and L4 info. If I have a bundle access Ethernet attachment circuit, and that is going out over a pseudo wire to a remote destination, whether that be for VPLS or VPWS, then what we're doing is that basically we are using the pseudo wire label. even though the PE may insert a FED label, we are not using that, unfortunately, in order to select the member on our upstream bundle. So that basically means that each pseudo wire on the PE device in an L2 VPN scenario will basically has pseudo wires per member. Okay. We have a feature request for that outstanding. I don't have a definitive release as to when that is going to change, but just so you know. Yeah, so basically, but this is what I was saying. The FED pseudo wire label is only used for P or core routers, unfortunately, today. Control plane architecture. This is another nice overview whereby, is that, of course, we have all our routing protocols. The routing protocols run on the RP CPU, whether that be in BGP, ISAS, OSPF, ERGP, static. They all feed into your RIP, your routing information base. Your routing information base is then being distributed down to your Linecards CPU and thrown into the what we call the software FIB, or forwarding information base. And this gray arrow between the RIP and the FIB is that Ethernet out-of-band channel, right? So if we were to talk about the concept of clustering 9Ks, and I had that EOBC Ethernet port on my RSP, basically I'm plugging a cable right into that gray arrow there, and I'm basically able of taking out the RIP contents and push it down to another node so that they both have the same view about the routing table, right? So that's how that works. So the software FIB basically needs to be completed with a layer 2 rewrite string, right? And that comes from the what we call the AIB, or JCC information base. Lots of TLAs here, 3-letter acronyms. It needs to be interesting. And the AIB is being fed by ARP. So another thing here is when we're talking about distribution of capabilities of the 9K, here you can see that ARP is completely distributed to the line cards, okay? And that's perfectly normal, because an Ingress line card, why would it need to know the MAC address of an interface on a total different line card? It's a waste of memory. So this way, by distributing ARP, we are basically able of, we have tested it, or we officially support 128K ARP entries per line card CPU. However, this is being put in shared memory. If you don't use that shared memory for other heavy hitters, such as NetFlow with 1 million cache entries, you can basically increase that ARP table, or the adjacent information base for that matter, to even 500K without any problems. But, it all depends on your shared memory capabilities there on your LC. Some show commands associated with that. The RIP, show route, that is no surprise. The AIB, you can see with the command show adjacency. And very important is that you use the location keyword here. If you omit the location keyword, by default, you're looking at the RSP, okay? Otherwise, it's because of the distribution of XR, that's why we need to provide the location keyword in order, to instruct the show command effectively where to pull that info from. The software FIB, show Ceph, very important. And we can also zoom into the LC MPU with the command still show Ceph, but with the command hardware. And because we have been talking about the fact that the FIB lookup for Ingress is different than egress, right? The data provided between the two is substantially different. So that's why you also need to provide the hardware Ingress or the hardware egress command in order to identify which direction you want to look at. Now, I've been talking a little bit about the white papers and technical articles that we have been that are applying to the various slides that we have been talking about here. And this is basically a summary of all the different things that we have been writing about. And we would really like to invite you, to use this Cisco support community. Ask us questions about the 9K. We'd be happy to provide you pointers or give you a write-up in case you're very interested in a particular topic or technology or how the 9K implements it. So next sessions probably are going to go way deeper into the FIB architecture, how to troubleshoot that. However, we have great articles available that talk about the show Ceph commands and how to interpret that data that is being provided, right? one of the most important articles is the ASR 9000 packet troubleshooting article, and you will see a lot of pictures reappearing that we have been seeing here today. It provides you also all the show commands necessary, like in order to follow packets going through the system. And hopefully, like this session today gave you a little bit better understanding, as to how everything ties together, and then you read those articles, that those, all that terminology starts to, make sense and line up for you. All right, more articles, and that is basically the session for today.
Excellent. Thank you, Xander. Okay, now the time that everyone's been waiting for. It's time to get to our questions from our audience. By the way, if you can't stay with us all the way through the Q&A, be sure to click on the evaluation that will pop up once you do close your browser. This survey will help us determine how this webinar met your business needs and expectations. Okay, let's move ahead to the Q&A. First question. Are there any modules or cards that perform CWDM or DWDM functions?
Yes, all the line cards support IP over DWDM. So you can configure that, no problem. When PHY is being supported also, CWDM can also be done. For that we have different optics. Either you can use a colored optic with a fixed wavelength, or we have tunable optics that you can select the wavelength on by means of configuration. We also have the ability to do G709 FEC and EFEC. However, that requires a software license, and that is supported on all the Typhoon line cards, but only on the Trident line cards, the 2T20G and the 8x10.
Okay, very good. Okay, we have a question regarding the expectation of the 8x10 gig MPA. When will that be expected, and will it be line rate?
It will be a line rate if you will put it into the Mod 160, because the Mod 160 gives you 2 NPUs. So then we can do 1 NPU per 410 gigs out of that MPA. And that MPA is scheduled to be released along with XR 431, so this month pretty much.
Okay. All right, another question here. Again about CWDM or DWDM. In operation as multiple gig in, MUX internally, and 1 fiber out with multiple wavelengths on the line card corresponding to the inputs.
Ooh, I'm not sure if I understand that question. Can you say that again?
You know what? I'm a little confused myself. I'm not sure. Yeah, it is not so much worded as a question. Okay, well, we'll have one of our question managers take a look at that one.
Okay, perfect. No problem. Sorry about that.
No problem. Is there any rule of thumb to decide the bandwidth for data plane in NV cluster? Say that one more time. I'm so sorry. Is there a rule of thumb to decide the bandwidth for the data plane in the NV cluster?
Okay, great. Yeah, good question. Well, is that I think we should also organize a webinar one time about the NV technology, whether that be satellite or clustering, to go into that into a lot of depth. To give you the short answer is that generally the 2 nodes of the cluster will do what we call rack locality. So we will also always try to prefer the local member of the bundle, or the local ECMP path down towards the CE or the subscriber for that matter. So in that case, the inter-chassis bandwidth requirements are very minimal. Only single home devices basically will start using that inter-rack link or IRL when the packet is being received on the peer node. So it really depends on the amount of CEs and the bandwidth requirements that you have on those guys, times the fact, is that how many are single homed, which would basically, constitute your inter-rack link requirements. What we advise is having at minimum 2 10 gigs. The reason for 2 is that redundancy, because the IRLs or interrect links are also used for keep alives for both nodes to detect that they are still alive. So 10 gigs minimum, and then from then on, it really depends on the bandwidth requirements for your Cs.
Excellent. And as just a reminder to everybody, Xander will be participating in the Cisco support community forums over the next 2 weeks. So if your question didn't get answered or you have some new ones, you can always check back and post it there. Now to the next question. Are there any Cisco labs available for the ASR 9K?
Great question. Well, is that one thing that we do recognize is, is that iOS XR is maybe a little bit of a complex operating system, and that there is a lot of need for training environments, right? So we are trying to make virtual routers available that basically allow you to get familiar with the iOS XR operating system, how to configure things. It is basically from a control plane perspective, so the underlying hardware is not really the 9K for that matter. If you are interested in getting familiar with the 9K platform specifically, for that, we would want to recommend getting in touch with our training partners who have an ASR 9000 Essentials training, for instance, and that will go into very much depth on how to configure the 9K and the 9K specifics if the virtual router for XR is not accommodating the need.
Okay, next question. When using certain features like ACLs or security, and then using super frames, will that impact any type of performance? And if so, can that be disabled?
No, super framing is implemented in the hardware of the FIAs, the Fabric Interface ASICs. We also don't have any show commands available that can tell us, how many packets have been aggregated into a super frame. The question has been raised before. We have evaluated, whether that makes sense from a troubleshooting perspective or what the value add from that is. We found out, that there is not that much value add in it. It would degrade the performance effectively by exposing or by creating counters like that. So that's why we don't have that ability. So super framing by itself provides the efficiency of fabric forwarding, and it doesn't have any performance impact for that matter, no.
Okay. Here's a question on the ASR 9001. So if the 9001 supports 80 gigs, that's 2 by FIA. So if I'm using all 4 by onboards on all 4 onboard 10 gig ports, I can really only use 2 by 20 by 1 gig MPA to keep from oversubscribing. Is that correct?
Well, yeah, it depends, right? And let me explain to you why it depends. So in the 9001, we have 2 NPUs, and these NPUs each serve 2 of the 4 onboard 10 giggies, right? So knowing effectively that the Typhoon NPU can do about 60 gig and 44 million packets per second, that basically gives me, with the 2 10 gigs that are fixed, gives me 40 gig worth of bandwidth out of that NPU still available for the bay. So I can either use a 1 by 40 gig, or a 4 by 10, or a 2 by 10, or a 20 by 1, and I would not oversubscribe the NPUs there.
Okay. What is the default queue buffer size?
That depends on the QoS configuration, and I generally hate the word "it depends," so let me try and get a little bit more specific answer here. So each NPU, we saw that each NPU has this frame memory attached to it. The frame memory is where the buffering of packets is in. On the Trident -L and -B cards, this is for 50 milliseconds worth of traffic. For the -E cards, it is 150 milliseconds worth of traffic maximum. On the Typhoon-based line cards, and I have to dig in my memory here, it is about 3 times as much. So it is about 300 milliseconds per NPU. And the way that it is being carved out, it is basically first come, first serve, right? So if I have on my Trident line card, if I have one interface to my NPU, then that one interface can use either the 50 or 450 milliseconds worth of buffering. If I have created two sub-interfaces here, well, then that 150 milliseconds is being shared by those two sub-interfaces. And then it depends on my queue limit configuration in my QoS policy map, how much I want to allow from that buffer to be assigned to that interface. And I can allow oversubscription. There is no problem with that. But then you'll run into packet anarchy at some point, of course. But technically, that is all possible. And I want to mention, by the way, if you Google ASR 9000 quality of service architecture, you'll find a great write-up on discussing that particular topic also.
Okay, excellent. Next question here. How many of your customers are using NV at the internet edge and not BGN? We're looking into implementing that at the edge and trying to understand how this is embraced by the community.
NV Edge clustering is a very popular concept. There is a tremendous amount of interest for it. It is one of the better things that we could have done. The thing is, is that clustering has been rather new. A lot of customers are deploying it, especially here in the US region that I mainly serve. We see, a lot of providers, leveraging this capability. So it is definitely something worth considering and embraced by the community.
Okay, I think we got time for just one last question. Is there a shortcut for a bundle Ethernet X interface like POX in iOS?
Great question. I'm so glad that it comes up. I've been asking for that multiple times myself. Let me, one of the things, as much as I love XR and 9K, right? The one thing that I don't like is the fact that the word bundle Ethernet is many times abbreviated in a show route, for instance, with BE. BE 100, and if you want to copy paste something, that BE doesn't work, right? So we have an outstanding usability requirement open to basically allow exactly that we can leverage the keyword BE for bundle Ethernet. Which release is that going to show up? I can't make a commitment on that as of now, but it is definitely one of the usability enhancements that we're putting a lot of fire on. Yeah.
Okay, very good. Great question. Okay, we just want to say thank you for your feedback today, and just a reminder, everyone who does fill out the evaluation form will be entered to win a $50 Amazon gift card. So please don't forget to fill out your surveys. And as promised, here is our trivia question. What do Cisco router technology, McDonald's, and Disney have in common? In this same year, Cisco earned its first patent for its method and apparatus for routing communications among computer networks. Also, the first McDonald's in Beijing, China opened, and Euro Disney opened in France. What year was it? See if we can test your memory. And we'll get to the answer in just one moment. And as I mentioned, Xander will be participating from May 14th to May 24th in the Cisco support community. As always, you can watch the recording of this webinar in the next coming 5 business days, as well as all the Q&A will be posted as well. Please join us for our next webcast in Russian. That's coming up on May 21st, Configuration and Features of Border Gateway Protocol, Independent Convergence. Also, we have one in Japanese, Cisco Catalyst High CPU Troubleshooting Training, and that will be on May 28th. And our next webcast in English, Configuration, Design, and Troubleshooting of the Cisco Nexus 1000, taking place on Tuesday, June 4th. And here are the current Ask the Expert events in English. These are currently running on the Cisco support community. And coming up on June 25th to the 27th in Cisco Live 365, we'll have the virtual event for Cisco Live 2013 in Orlando. This will be the hybrid event that goes along with the physical event taking place in Orlando, so please do join us. And of course, we invite you to participate socially with the Cisco support community across all the different social networks. And of course, in our other languages, Spanish, Portuguese, Japanese, Polish, or Russian. And here is the answer to our trivia question. correct answer, and it looks like the majority of you folks got it correct. It is A, 1992. So congratulations if you got that correct. We want to thank everyone for your time today. Thank you, Xander, and thank you to our question managers, and we wish you a great week. Thank you.